In this video, we're going to ask what it takes to make a planet habitable. Now, there are many things needed. We don't want the mass too high or too low. If it's too high, the gravity will be so intense. If gravity is too light, there'll be no atmosphere. You want a solid surface. But most important of all is probably the temperature. Life as we know it requires liquid water as a solvent in the bloodstreams and as the working material to allow all the carbon chemistry. Now, it could well be that life in space maybe somewhere doesn't rely on it, has some other solvent, but let's be conservative and say a planet might be habitable if it can have liquid water, in which case the temperature has got to be greater than 273 Kelvin and less than 373 Kelvin. But what determines the temperature of a planet? Well, here's a planet. By temperature of a planet, what we really mean is the temperature of the thin surface layer, the atmosphere, the plants and so on. We don't really care about the temperature in the middle. Middle of most planets is huge amounts of lava. But it turns out all the heat from that seldom leaks through to the surface. What controls the temperature of the surface is the balance of heat in and heat out. You get heat in, which is radiation from the star that the planet orbits around, and heat out. Any object will radiate heat. This is called black body radiation. Everything does it. You're doing it as you sit here watching. I'm doing it as I sit here writing. The black body radiation is given by the Stefan-Boltzmann equation, which is the power out equals the surface area, a constant called the Stefan-Boltzmann constant, t to the fourth. The Stefan-Boltzmann constant is 5.67 times 10 to the minus 8 watts per meter squared, Kelvin to the minus 4. Now, this assumes something is actually jet black. If something is actually not jet black, and most things aren't, there'll be an extra constant in here which reduces the amount of radiation coming out. But for the moment, just assume that constant equals 1. Crude approximation. So that's the heat going out, which depends on the temperature. How about the heat coming in? Well, if you've got a star with a known luminosity, we can calculate using the inverse square law the flux, which is the flux amount of radiation per unit area going over here. But what's the area of a planet? It's a sphere. The bit that's face on the equator, that's the energy per unit area will just be the flux, but a bit near the poles it'll be much smaller. What you can do, however, is approximate the planet as a disk of the same radius facing the star, because all the radiation that would have hit the surface of the planet will hit this disk, and it's easy to calculate because it's all face onto the star. So the radiation, or the power in, is equal to the flux times the surface area, which is pi r squared, if r is the radius of the planet. Now, that's assuming that all the radiation is absorbed. In practice, we need a little constant in here as well, because some will be reflected, especially if you've got something like clouds or polar cap. But once again, we'll assume that both these constants are 1. In reality, they won't be, but it will give us a rough idea of what's going on. We also know from the inverse square law that the flux is equal to the luminosity over 4 pi d squared, where d is the distance between the star and the planet. So let's set these equal to each other. So we get the power in, which is flux times pi r squared, equals the power out, which is a, the surface. For the power out, the area is the entire surface area. So surface area of a sphere is 4 pi r squared. Sigma t to the fourth. So we can cancel some pi's, cancel the r squared, and rearranging we find that temperature is going to be the fourth root of L over 16 pi sigma d squared. So that will tell us the equilibrium temperature we expect for a planet. That's if the energy in equals the energy out. What happens if energy in is bigger than energy out? Well, in that case, as there's more heat coming into the surface than going out, it will get warmer and warmer. That means the temperature will rise, and the temperature rise means the power out will get larger. So eventually the power out will match the power in, and it will settle down to a new temperature. If the power in is less, the temperature will drop, more will be radiated. The temperature will drop until once again they come into a balance. So that's our prediction. How does it work in our own solar system? So here's our prediction. The blue curve here is the curve we've just calculated, and this is for our own sun. So what you see is the temperature goes down as you go away from the sun, as predicted. So if this was correct, it tells us that the habitable zone for our own sun would be about from about here. So it's about 0.6 AU out, which is where our equilibrium temperature would go below 100 centigrade, so water would cease boiling, and down here, about 1.1 AU. So this is the habitable zone. Too hot and too cold. How does this match the actual data in our solar system? Well, here are the planets. That's Mercury, Venus, Earth, and Mars. And you can see that Earth is in the habitable zone, which is kind of nice. We're right near the outer edge. We're nearly freezing according to this. And in fact, you can see we're a little bit above the line. The Earth is a little bit hotter than is predicted by this model. That's because the amount of radiation coming out from the Earth is blocked primarily by water vapor in the atmosphere, a natural greenhouse effect, and keeps us a bit hotter than would otherwise be. So that's good. Earth is habitable. We knew that. How about the other planets? Well, Mercury is clearly too hot. Mars is clearly too cold. Venus, though, it should be right in the middle of the habitable zone. But instead, it's incredibly hot. Far too hot to be habitable. So this calculation is clearly a bit too simple. In the case of Venus, it has a runaway greenhouse effect. It probably did have oceans to begin with, but they boiled. The hydrogen escaped into space. Oxygen combined with the surface. Leaving a huge atmosphere of sulfuric acid and carbon dioxide, which makes it far, far too hot because of a very strong greenhouse effect. So, how good is this theory? It gets 3 of the 4 inner planets in our solar system pretty accurate. Completely stuffs up on one of them. In our solar system, according to us, there should be 2 planets in the habitable zone. In fact, we've only got 1. So, it's clearly a rough guide, but not very accurate. However, it's the best we've got for the moment.